So there's a tremendous amount of energy that is released in a nuclear fission reaction. Where does it all come from? Well, it comes from matter being converted into energy. So if we look at uranium-235 bombarded with a neutron, splitting into barium-140 and krypton-93. If we look at the masses of these particles and add them up, we find that there is a difference in the mass. The total mass of the products, 235.86769. Total mass of the products, reactants, 236.05258. Right, so let me do the math real quick there. And normally we'd look at that and say, oh, well, that's like really, really close, good enough. But not good enough. Oh, well, that didn't work out at all. Turns out you actually have to put all the digits in. Yeah, so we've got, you can do the math as well. What I'm coming up with is a loss of mass equal to 0.63759 atomic mass units. Anybody else get that? Anybody else have a calculator? I just took this this number and subtracted that one. Yeah, just the difference in mass between the products and the reactants.
How about
0.1848. So, anybody else? Yeah, the second time I get 0.18489. So going for best 2 out of 3, that one's wrong, and this one's correct. Okay. So there is a difference there, and try to remember what we learned in Chem 1A about significant figures. So when a chemist expresses a measurement like this for the mass of this particle, where's the uncertainty in the last digit? So this is implying that we have measured this and we're confident about it to the nearest plus or minus 0.00001. That there is uncertainty in the last digit, right? And so all of these were measured far more precisely than we usually express measurements, right? When we do calculations, especially the problems from the textbook, a lot of times they've got like 3 or 4 sig figs in them, right? Which is good enough because we're illustrating a process, right? That is not as precisely as possibly we could measure them. So here, these are being measured very precisely because here it's very important. So if we're doing, if we're comparing significant figures, I think all of these have at least 5 decimal places. And so this number is correct here. That is a real difference in mass. So what happened to the mass? It was converted into energy. So the rules that we've learned, the laws that we've learned before about law of conservation of mass, in a chemical reaction, mass is neither created nor destroyed. This isn't a chemical reaction. This is a nuclear reaction. We excluded nuclear reactions from that law. Law of conservation of energy. In a chemical reaction, energy is neither created nor destroyed. Energy is being created here. It's a nuclear reaction. So for nuclear reactions, we have to combine those two laws, law of conservation of mass and energy. Combined, those are always conserved. Any questions about that? I know it's a little strange. So you've probably seen this equation, E equals mc squared. Who came up with this? Einstein, Albert Einstein, very famous for this. We throw this around a lot. We don't really think about what exactly does that mean. Well, E is energy, M is the mass that is lost, and C is the speed of light. So the energy produced in this fission reaction is equal to the mass that's lost times the speed of light squared. I don't know about you, but it seems really odd to me that the speed of light squared gets involved in this. But there it is. This is how it works out. So we can calculate the energy produced in the fission of one uranium-235 atom, or nuclide. So we just calculated the mass that was lost. So the mass that was lost was 0.18489 atomic mass units. So to calculate the energy, we're going to take that mass and multiply by the speed of light squared. And we come up with a number. Now I just put in 3 sig figs for the speed of light. Whoops, got an extra digit in there. That is an answer. But what are the units on that? Well, they would be atomic mass unit meters squared per second squared. Not a very useful unit. We don't recognize that as a unit of energy, do we? What's the unit of energy that we usually use? Joules. So 1 joule is equal to 1 kilogram meters squared per second squared. So comparing this messy unit to this messy unit, the difference is that this is atomic mass units and this is in kilograms. So could we convert atomic mass units to kilograms? Sure we could. How? Without asking Siri or Google or looking in the textbook. Could we figure that out? What do we know about atomic mass units? Do you remember the definition? An atomic mass unit is 1/12 the mass of one carbon-12 atom. Yeah, everybody remembers that, right? It was defined that way because carbon-12 has is stable, common, easy to work with, etc. And so the result of that is if carbon-12 weighs 12 atomic mass units, then it has 12 what do we call those? Nucleons, right? Protons and neutrons together. So each of those particles ends up equaling 1 atomic mass unit, approximately. The The mass of 1 mole of carbon-12 is 12 grams, right? So what does that mean? Well, 12 atomic mass units and 12 grams per mole, right? The mass of 1 mole of atoms is 12 grams. This is the mass of 1 atom. So how much in atomic mass units would a mole of carbon-12 weigh? How about if we took, so we have 1 atom, right, of carbon-12, and that weighs 12 atomic mass units per atom. And we want a mole of these. So what do we multiply by? Avogadro's number. Oh. So that's going to give us atomic mass units per mole. Oops, don't cross that off. What did I do? I think I didn't want this up here. Yeah, so 12 atomic mass units per atom. That many atoms per mole, and looking at carbon-12, 12 grams per mole. Yeah, those cancel. There we go. And now we've got atomic mass units related to grams. The 12s cancel out, don't they? So we get Avogadro's number of atomic mass units equivalent to 1 gram. It's not an accident. That was set up that way. So can we convert atomic mass units to kilograms? Sure we can. Okay, now that I made all that mess, let's get rid of that. So I need some room. Okay, so we've got 1.66 40 times 10 to the 16th atomic mass units meters squared per second squared. Going to multiply by 1 gram per 6.022 times 10 to the 23rd AMUs. And then we need to get to kilograms. So we want kilogram up here, and a kilogram is 10 to the 3rd grams. So that gets us 2.76 times 10 to the minus 11 joules. That's for 1 atom. Any questions? If you're a little rusty on unit conversions like this, come talk to me and I'll give you a refresher. So let's look at the formation of helium-4 from its components. Taking a helium-4 atom, looking at, well, what are the subatomic particles in there? What do those weigh? And let's add them up and see what happens. So we've got in a helium-4 atom, well, we're looking at the nucleus, not the electrons. So a helium-4 nucleus is going to be 2 protons, which is essentially 2 hydrogen nuclei, and 2 neutrons. So here are the masses of the proton and the neutron. We can add those up together. And here is the the alpha particle, the helium-4 nucleus, and this is its mass. The mass of the actual nucleus is less than the sum of its parts. This is called the mass defect. And again, this is not just small errors in measurement. This is a real difference in mass. Where did the mass go? What can mass turn into? Energy. So the energy that corresponds to that mass defect is called the nuclear binding energy. And that's the amount of energy it would take to break a nucleus into its components, the protons and neutrons. Does that make sense? I mean, something's got to hold these things together, right? And it's got to involve energy. So nuclear physicists often use a unit called the electron volt to report energy. And an electron volt has the abbreviation EV, capital V for volt and E for electron. An electron volt is the kinetic energy of an electron that has been accelerated through a potential difference of 1 volt. So that is a unit of energy. A mega electron volt would be 10 to the 6th electron volts, and that is equal to 1.602 times 10 to the minus 13 joules of energy. So there's this relationship. We can also relate atomic mass units to mega electron volts. On Thursday, some of you were asking a question about one of the worksheet problems, and I kind of sketched this out on the board. You can actually do this calculation. It's similar to what I just did with the mass that was lost in the fission of uranium. But you can take one atomic mass unit and convert that to energy using Einstein's equation, E equals mc squared. You'll get that silly unit of atomic mass unit, meters squared per second squared, which you can convert into kilograms meters squared per second squared. And you can use this relationship to get into mega electron volts. And that's where this comes from, is converting this amount of mass into energy. That's the conversion factor. Now, I do not expect you to remember those 2 conversion factors. So those will be given to you on an exam. But I do expect you to remember, capital M, lowercase e, capital V. You should know what that is. It's a mega electron volt. So the mass defect for helium-4 is 0.03038 atomic mass units, which if you had done the math on that slide, that's what we would have come up with. What's the nuclear binding energy? So this is the amount of mass that was lost, apparently, when you put those things together. So we like the equation E equals mc squared. We've heard it before. It's nice and everything. And so you tend to want to go to that to solve a problem like this. But that actually is going to be the long way. The short way is just to use this conversion factor, 1 atomic mass unit is equal to 931.5 mega electron volts. 931.5. So we can just convert units here. 931.5 mega electron volts per 1 atomic mass unit. We get 28.29897. Now I know that earlier in the semester we got really sloppy with significant figures. We kind of just used 2 or 3. Here we should try to remember the rules and get back on track. This number has 4 significant figures. Leading zeros don't count. This relationship is not an exact number. 4 significant figures as well, so then we should report this to 4 significant figures and call this 28.30 mega electron volts. The nuclear binding energy of a helium-4 nucleus. Any questions? So that's for one helium-4 nucleus. It can be helpful to look at binding energy per nucleon. Remember, a nucleon is a proton or a neutron. It's the particles that make up the nucleus. So if we looked at the binding energy per nucleon, how many nucleons are in a helium-4 nucleus? 4. The number of nucleons is the same as the mass number. So if we take this and divide by 4 nucleons, then we get the binding energy per nucleon. And that allows us to compare between different, sizes of nuclei. So mega electron volts per nucleon. So that's 7 mega electron volts per nucleon. The larger the binding energy per nucleon, the more stable the nucleus is. Calculate the mass defect and nuclear binding energy per nucleon in mega electron volts for uranium-238, which has a mass of 238.050784 atomic mass units. So how do we calculate the mass defect? We're given the mass of the actual nucleus. We have to calculate the mass of the parts, right? So we're going to need the mass of a neutron and the mass of a proton. And again, these are also things that you just don't remember off the top of your head. But we can pick them up from this slide. I'm going to write them on the board because that's too many digits for my brain. So a proton, 1.00783, a neutron, 1.00866 atomic mass units. Oops. Okay, so uranium-238. Uranium-238. How many protons? 92. Its element number 92. Its mass number is 92, so we've got 92 protons. How many neutrons? 146. So 238 minus 92. 146. Right. 238 minus 92 is 146. So we have 92 protons times the mass of a proton And we have 146 neutrons times the mass of a neutron. (92 times 1.00783). 92.72036. One, two, three, 4, 5, 6, 2. Atomic mass units. And 146 times 1.00866. 147.26436. 6 sig figs. There we go. And then we're going to add those together. To 39.98472 atomic mass units. The actual nucleus weighs 238. So we're going to take the sum of the nucleons, the expected mass, and subtract the actual mass. And we're going to come up with 1.933936 atomic mass units. That's the mass defect for uranium-238. Any questions? We're dealing with a lot of digits here, but the math itself is actually quite simple. How many particles, how much do they weigh, multiply, add them up, compare that to the actual mass. And then nuclear binding energy per nucleon in mega electron volts. So we're going to take the mass defect, 1.933936 atomic mass units, and how do we convert that to mega electron volts? 931.5 mega electron volts per atomic mass unit. Of course, I don't have enough space there. So multiply by 931.5, which gives us 1801.461384. Way too many digits. Per nucleon, what are we going to divide by? 238. The number of nucleons divided by 238 nucleons. And we're going to get 7.569 mega electron volts per nucleon. So for the helium-4, we came up with 7.075. Here we've got 7.569. Higher nuclear binding energy per nucleon means this is more stable. Any questions? So if we calculate the binding energy per nucleon for different isotopes, different nuclides, we can see as the mass number increases, there's not like a nice linear relationship or anything. Here's deuterium, and here's helium-3. Those are both not very stable. That's why you're not familiar with them. Here we've got helium-4, lithium-6, carbon-12. The maximum comes at a mass number of 60, which is right in here. Iron 56 is real close to that. And then as we get to larger and larger ones, this binding energy per nucleon starts to go down again. So this yellow band here, those are the most stable nuclei. So the maximum there is there at 60. And what we've got indicated here is that the smaller nuclei will undergo fusion to make a more stable nuclei, and the larger ones will undergo fission, splitting, to make more stable nuclei. So if you break a heavy nucleus into lighter ones, that's an exothermic reaction, because you're taking less stable and breaking it and making it more stable, so that's going to release energy. And if you combine two light nuclei into a heavier nucleus, that's also going to be exothermic. It's going to release energy. So fission and fusion are both highly exothermic.